Okay, welcome to another fun-filled video of verifying identities. In this video, I'm going to work through two examples, both of which are verifying identities using a combination of the sum and difference identities along with the double angle identities. Okay, so what these verifications are doing, or these proofs, are they're now combining multiple identity definitions together in order for you to manipulate and prove that one side equals the other side. Okay. Now the biggest advice that I can give with these is you usually want to start working on one side of your equation. Your goal is to make it look like the other. So what I always tell students is pick a side to start with. Pick a side that when you look at it, you automatically have some idea of where you may start. Don't pick the side that looks complicated. Pick the side that looks like you can easily manipulate it. So if we look at this first example, I have the tangent of 3x equals this whole mess of stuff. Well, not once, or not up to this point yet, have we really talked about powers of trig functions. And so since we don't really have that at our disposal, and because it does not appear as though this right-hand side can be easily factored, or factored into a way that's going to help me at all, I'm going to focus on this 3x part. Now one thing I know is that I can take 3x and I can break it into an addition problem. So I can take the tangent of 3x and I can say, okay, what if I turn that into the tangent of 2x plus x? Now the reason I'm going to do that is because this may give me a double angle and this thing gives me a sum, which gives me a place to start. Okay, so again, my goal is that this is going to equal this left-hand side. Okay, so in this proof, I'm just going to write equals here. I'm not going to keep writing this fraction over and over again. Just realize that that's what goes here. Okay, is my proof. So I'm going to expand this. So one of the things I have to remember is that I have just stated that u is going to be my 2x and v is going to be my x. And I'm using my sum identity for tangent, which says I'm going to have the tangent of u, so 2x, plus the tangent of v, so x, all over 1 minus the tangent of u, which is a 2x, tangent of v. So if you look at what this is supposed to equal, notice on the bottom I have this 1 minus piece. So I think I'm probably on the right track of what I'm supposed to do. Now I have this double angle piece, and so I'm going to go ahead and use that. And so with my double angle, I'm going to use the tangent version of my double angle here. And so I'm going to turn this tangent of 2x into 2 tangent of x over 1 minus tangent squared of x. And then this is still plus the tangent of x. And this is still all over 1 minus. But now again, I've got this tangent of 2x that I'm going to transform. So this becomes 2 tangent of x all over 1 minus tangent squared. And then this is going to still be times the tangent of x. Now the reason why I chose to use this version of the double angle is because my result here, what I'm trying to get to, only has tangents in it. So I want to make sure that I'm using something that only has tangents in it. Alright, so now I have this whole big mess that I'm hoping is going to equal what I want. So I just have to start combining using my common fraction knowledge. So if I look just at the top, I need to have a common denominator here. my common denominator is going to be 1 minus tangent squared of x. So that means I'd have to multiply this side by that denominator. So when I combine, I get 2 tangent of x plus, this is then going to be the tangent of x minus the tangent cubed of x, and this is over 1 minus my tangent squared, and the whole thing is over my denominator. So let's look at this denominator here. So in my denominator, first I have this multiplication, so this is really going to become tangent squared on this side, and then I got to turn this 1 into that denominator. So here I'm going to end with 1 minus the tangent squared of x, and then minus 2 tangent squares of x, and this is going to be over that 1 minus tangent squared of x, and I'm hoping that this thing equals. So right now it looks like I've made a total mess, but in reality I actually haven't done that bad. So first and foremost, one of the things I know is that when my two denominators are exactly equal, they cancel out, and what they leave me with is what was on my two numerators. Okay, so here if I look at this numerator, I have 2 tangent of x plus the tangent of x. So this tells me I have a total of 3. So this is 3 tangent of x, and then I still have this minus my tangent cubed. I've gotten rid of these two denominators here, and now let's look at this numerator. So I have tangent squared minus 2 tangent squared, so this is going to end up being 1 minus 3 tangent squared of x. Now if you look at what we started with, we started with my value, which said 3 tangent of x minus the tangent cubed of x all over 1 minus 3 tangent squared of x. So if you look, notice what I manipulated on my left hand side equals the right. Thus, this verifies the identity, which says that I now have a new identity. So what I just did is I have now proven a cubic angle, or what can be called as a triple, in that the tangent of 3x does indeed equal 3 tangent of x minus the tangent cubed of x all over 1 minus 3 tangent squared of x. So this, in a sense, is what you actually did, is you proved the identity by showing that both sides equal. Okay, and so that's what we're doing here. We are proving identities that might be bigger or a lot different than what it was we started with, using the identities we already have. Okay. Alright, so let's look at another one that's kind of a little bit different. So here I've got the sine of 3x over the sine of x, and I want to show that that equals 3 minus 4 sine squared. So the first thing again I want to do is I want to use this more, this left hand side, this more where I have an angle that I can work with. Okay, here again I haven't really done anything with powers, and so I would use my right hand side to be what I want it to equal or prove to. So the first thing I'm going to do is split it. So this is going to be the sine of 2x plus x, and this whole thing is still over the sine of x, and I'm hoping that equals what I want. Now with this, again, I have identified that my u term is 2x and my v was x, and this again is a sum. In this case, it's the sign for sum. So here, this is going to become the sine of 2x, the cosine of x, plus the cosine of 2x, the sine of x. And this whole thing is still over the sine of x. We need to input for our double angles. So the first is we need to change sine of 2x to being 2 sine of x cosine of x. And then we're going to have plus. Now here's where things get a little tricky. If you remember, cosine of 2x had 3 choices, and you have to be very careful at which choice you choose. Now, in looking at it, I have this sign on the bottom. And when I look here at my results are just in sign. So I would lean more towards trying, and that's, notice I said try, because when we're dealing with double angle for cosine, sometimes you may try the wrong version. So this is just trial and error. So we're going to try the version that is only sine. And what that means is that the cosine of 2x can be rewritten as 1 minus 2 sine squared of x. And then we've got times that sine of x. And the whole thing here is over the sine of x. Okay. So again, remember, here for this 2x, you need to choose very carefully. But it's all about trial and error. So what I can tell you here is if you pick the wrong version for cosine of 2x, come right back to this step, change the version in here, re-manipulate, and see if you get what you need. Okay. Alright, so we still have some issues, and so let's see if we can kind of try and work them out a little bit. First things first. I forgot my cosine. So first things first is we have to do some simplifying here. I have a sine and I have a sine, and I've got a sine on the bottom. So one of the things I know with fractions is that I can cancel these out by pulling the sine out to the outside and then getting rid of it. So this is going to leave behind 2 cosine squared of x plus 1 minus 2 sine squared of x, and again I'm hoping that that equals what I want. So now looking very carefully at what I have, I want to recall an identity. So right here for my cosine squared, I want to recall my Pythagorean identity. That identity said sine squared of x plus the cosine squared of x is equal to 1. And I'm going to use this identity to interchange the cosine squared over to sine so that I have just one trig function I'm working with. So if I take this identity and subtract the sine over, I can rewrite it. So this becomes 2 times 1 minus the sine squared of x plus 1 minus 2 sine squared of x, and I'm hoping this equals. Distributing the 2 through says I have 2 minus 2 sine squared of x plus 1 minus 2 sine squared of x. Combine my terms. I've got 2 plus 1, that's going to give me 3. I have negative 2 sine squared, and negative 2 sine squared gives me minus 4 sine squared of x equals, and then I need to look, and what exactly did I have to start with? I had 3 minus 4 sine squared of x. So just so you see, here we go, 3 minus 4 sine squared of x. So I proved my identity. Okay. So again, when we looked at it, the identity that we proved was that 3 sine of 3x over the sine of x equals 3 minus 4 sine squared of x. Okay, so in other words, this is your identity. This is what it equals. Okay, so when you're proving these identities, it's a good idea to kind of keep track of what it is that you were kind of proving and what it is that you're showing that it equals. And the reason for that is because down the line, the further that the identities build and the more you have to work with, the more you'll be able to look back on some of these other identities you've proven and be able to interchange them around. Okay, kind of like the fact that we are able to take the sum identity and then also reference back to the double angle identity in order to make this proof. Somewhere else we may be able to reference this identity in order to prove something else. Okay, so make sure you're following what the identity is you're working with and what it is that you're proving that it equals. Again, if you have any additional questions or if you need to see any additional examples, please let me know. Otherwise, remember to be creative. There are multiple ways that you would be able to solve and prove your identities. This is just only one such example of proving it. Obviously, there are other methods or other approaches, so please feel free to use your own approach. If you're not sure if your approach is a correct one or if you think you've made a mistake and you would like a little input, let me know. I'd be happy to take a look. Otherwise, I look forward to seeing you next time.